So we saw the magnetic field around a straight conductor. What if we have a coil of wire? And this will create a device that's very useful in industry called the solenoid, and we'll get into that in this lecture as well. So the magnetic field around a straight conductor is intensified if we bend the wire into a loop. So if we do that, in the center of the field, or in between those two ends of the wire, we'll actually have magnetic fields that will, or magnetic field lines that will kind of add their strength together and be stronger in the middle. This is the idea behind a solenoid. A curved conductor can create a magnetic field that is stronger in the center. The magnetic field can further be intensified by confining the effects of a number of loops. So instead of just doing one loop, if we do multiple loops, we now have an even stronger solenoid because the magnetic field in the center is strong. And it essentially acts as a bar magnet. There is a right-hand rule for solenoids as well. It's kind of the same thing as the right-hand rule for conductors. If you place your hand around the solenoid, your right hand, the curl of your fingers would be the direction of the current, but your thumb would point in the direction of your magnetic field. So what would be the north and south poles of each of these different images here? Because your thumb points in the direction of your field, and we're talking about a bar magnet, your thumb points in the north direction. So if we have, for A, the conventional current flow is from positive to negative, so you would curl your fingers around that and your thumb would point up for A. So your north pole would be at the top, your south pole would be at the bottom. For B, that's a battery symbol. The larger side of the battery is the positive terminal. The smaller side is the negative terminal. So your current would flow from here, through here, down, and then curl up and around like this. So that means that your current would be flowing this way, around, and your north pole would be on this side, your south pole would be on that side. In this case, this is our positive, and it flows to our negative. If I put my right hand on top of that and hold onto that with my thumb pointing to the left, that'll tell me that this is my north side, and this is my south side. You might be noticing something. I'll go with the last one, and then we'll finish it up. Here, this is my positive, that's my negative, so my flow is from positive to negative. So my thumb would point towards the negative terminal. That's the north side, and that's the south side. So in these situations, your negative terminal is your south side. Sorry, I should say that again. Your negative terminal is your north side. The positive terminal is your south side of your magnet. Here's another question. It says, determine the polarity of the poles for this electromagnet. So this is not not a bar magnet, but essentially it's kind of like two bar magnets. Our conventional current flow would go this way, and then it would go down here, across here, and then go up and down. So the polarity of these poles, in the first case, my flow would be from positive here to negative there, so my thumb would point down, so this would be the south side, that would be the north side. Over here, my thumb would point up, so this would be the north side. Did I say that right? So this would be, my thumb would point down, this is a south, and this is a north. What happens if the current flow is reversed? Well, then the poles reverse as well. Solenoids are important because not only can the magnetic field they create be turned on or off, but the strength and direction of the field can be changed. If we want to increase the strength of the field, we could increase the current flowing through the solenoid. Another way to increase it is we can add more coils. So we can increase the number of coils, and that would give us a stronger field. We could also use put a material inside the solenoid, and if it's a very magnetically permeable material, it could increase the magnetic effect as well. Here's some notes to copy down about a solenoid, which is really just an electromagnet. That's our term for it, solenoid. And the important thing to note is 3 ways to increase the strength: increase the current, increase the number of loops, or increase the core material, or add a core material that is magnetically permeable. Calculate the effect on the strength of the magnet in the coil when each of the following happens. So if we change the current from 2 amps to 5 amps, we've increased by 2.5. So we're going to have a 2.5 times stronger magnetic field. If we increase the number of loops, or rather we decrease the number of loops from 4,400 to 1,100, we've cut the strength by 1/4. And if we change the core from steel that has a permeability of 3,000 to iron that has a permeability of 8,000, we increase the magnetic field strength by 2.7 times, or 8,000 divided by 3,000. I think it's 2.6 repeated. So this question says, an electromagnet is able to exert a force of 150 newtons when lifting an object. We have 1,000 turns on this electromagnet and the current is 1.5 amps. The material in the core has a relative magnetic permeability of 2,000. What force will the electromagnet exert if each of the following changes are made? So the force is 150. If we change that from 1.5 amps to 6, let's put on our calculator and I'll show you how to calculate this. So the original amount of current we had was 1.5. So we have to do 150 times our new current divided by our previous current, and we get 600 newtons. Next part of this question. If we increase the turns, the coils from 1,000 to 1,400, so here we start with our 150 times our new amount of turns, which is 1,400, divided by our previous, which is 1,000, we get a 210 Newton force. What if we do both at the same time? So in this case, and there is no real equations for this, it's just working with ratios. We have 150 times 6 divided by 1.5 times 1,400 divided by 1,000. We have 840 newtons. Here's an example of a solenoid using a nail as our core. So because a solenoid magnetizes the core, we could also use it as a bar magnet or as an electromagnet. When we turn the current off, we can have an unmagnetized core. This is useful for, there's a number of different technological uses. One of them is a speaker. So with a speaker, we have a core that is made up of basically a ferromagnetic material, and the circular covering around that core is magnetized in such a way that it could be a north pole and the core could be a south pole. So what would happen if we keep changing the polarity, we can end up pushing that core in and out, and we can make beats by moving the air around that core. So by continually magnetizing and demagnetizing the core, we have it push in and out and in and out, and we can create music with some bass in it. Another thing we can do is create large electromagnets. You can see these at junkyards. Basically, the flat plate on the electromagnet is a magnetically permeable material. When electricity is flowing, that can become magnetized and pick things up, and when we turn the electricity off, it can then drop whatever it's carrying. This here is an example of a switch that uses it can demagnetize itself after it reaches a certain load. So here it says the U-shaped core is often used with a coil wrapped around each leg of the device. If the coils are wound in opposite directions, the legs become oppositely magnetized, and the lifting ability of the magnet is doubled. So this is this is the switch of an electromagnet. So that double coil system is the idea behind the electromagnet, the large electromagnet. Relays are another, this is what I thought we were talking about. A relay is a type of switch that it uses a solenoid or pair of solenoids to kind of turn on or off. There's a physical connection that's required to close the switch, and that physical connection happens when we have a magnetized core. This contact point is made when we have the magnetic field pushing this closer to close that off. When the electric field so this pushes that closed. When the electric field is broken, this spring kind of pushes it back in place, and the switch is broken. That's our electromagnetic relay. Electric bell works similar to the relay as well. The bell, when we have the magnetic field activated, we push this arm close to hit the contact here, to make contact with the bell, but that breaks the magnetic field. This springs the bell arm back towards here, which closes the circuit, turns the magnet on, then breaks this again and hits the bell, closes the circuit, breaks it, hits the bell, back and forth. That's how the electric bell works. And you can read these slides for further understanding. This is just another way to explain the electric bell, but here's what you can copy down for uses of solenoids. The rest of the questions on this lecture just ask you to explain kind of the things that we just talked about again. So you can go through them and just sort of talk through your solutions by yourselves. The questions in the textbook are also helpful for understanding how electromagnets are used in technology.